So, hello everyone. I'm Riccardo Manno, and I'm a final year PhD student at Bristol Composite Institute. Particularly, my research topic regards the numerical investigation of damage in ceramic matrix composites at the microscale. So, typically, CMC microstructure is characterized by a high level of heterogeneity. Therefore, it was necessary to build up a high-fidelity microscale framework to homogenize the physical properties and pass the information to the higher scale. So we developed a couple of algorithms which allows the user to build up these microscale representative volume elements with random distribution of fiber and other features within the microstructure. Next step, we apply kinematic or thermal boundary conditions, and through a statistical consideration, we define the RVE size, which guarantees the convergence of the homogenized properties, which are stiffness tensor, thermal conductivity tensor, and electrical conductivity tensor. Furthermore, when you consider damage in CMC, the effect of the interface material, which is basically a coating and closing the fiber, is allowing basically to achieve a tougher material response. Hence, modeling what happens at the interface was one of the main topics of this work. We built a cohesive frictional law, which has been validated thanks to experiment work performed in Oxford, giving a quite consistent correlation. We also modeled the presence of a small value of a load eccentricity and considered that this is not having any major effect on the test, as you can see on the right. So the top curve is without eccentricity, the bottom curves are without eccentricity. So furthermore, the quantification of properties like fracture toughness and frictional shear stresses happening at this scale was necessary to conclude that the topic about the interface material. Hence, with the materials group of Imperial College London, we developed a virtual experimental capability which allows the calculation of these quantities. Particularly, we developed this microcantilever beam test for mode 1 fracture toughness, where we used a cohesive layer to enforce the interfacial behavior between fiber and interface material. Displacement of the beams are fed to the model, and the crack length is then compared with the experimental result, allowing them to define the mode 1 toughness. You can see on the right-hand side of the slide the comparison between experimental and numerical results in terms of crack length, whereas values of toughness instead have been compared with analytical models. For what concerns mode 2 fracture toughness and frictional stresses, we use the unloading-loading push-out test coupled with a VCCT analysis at different level of Coulomb friction coefficient. This method allows to calibrate the crack length upon just stiffness response comparisons, and therefore find the range of allowed critical energy release rates and frictional coefficients. Results are consistent with mode 1 we found in the previous experiment and virtual tests, and fracture toughness in terms of fracture toughness, and we also agreeing with value reported in literature. Finally, we developed a continuous damage mechanics model for Abacus for the study of mini-composite response based on Christensen failure criterion. Microcomposites are basically single fibrous tow, typically used as representative specimen in the analysis of experimental analysis of CMC. In this case, we performed some comparison in the fiber direction between numerical and experimental tests, as you can see on the top right-hand side of the slide. Particularly, the comparison has been performed only for the load in the fiber direction. For obvious reasons, transversal direction tests cannot be performed experimentally at this scale. Therefore, only the numerical results is shown. We are now in the process of coupling all the capabilities developed in this work to have a full framework that models damage behavior in CMC. Furthermore, using some novel multi-scale approach, we will be able to scale up the behavior up to the mesoscale. If you want to know more about this research topic, please contact me at the following email or virtually visit my poster. Thanks for your attention.